Good morning, everybody. Let me welcome John Ellis from King's College London and CERN to deliver the first lecture on the standard model and beyond.
Okay, thank you very much. The standard model has been with us for some 50 years now, and of course it was only in 2012 that finally the last building block of the standard model seems to have been discovered. Of course, the search for the Higgs boson is not the only thing that's important in particle physics. And, well, first of all, we need to understand whether this particle that was seen in 2012 really is the Higgs boson, or whether it's possibly something different. And then, of course, we're all looking eagerly for physics beyond the standard model. So in these lectures, I'm going to be starting off with the road to the Higgs discovery. Then in the second lecture, I will talk about the work that's been done since the discovery of this new particle to really check whether it looks like the Higgs boson or whether it might be something different. For example, there were many suggestions before the discovery that maybe there might not be an elementary Higgs boson, there might be something composite, maybe there would be some dynamical mechanism for electroweak symmetry breaking. So of course those theories are not yet ruled out, but they're certainly tightly constrained by the data on the boson that was discovered, as I will discuss in the second lecture. Then in the third lecture, I will discuss a number of other further beyond topics. So my own favorite possible extension of the standard model is to include supersymmetry. Some people ask me whether I've given up yet on supersymmetry. The answer is no. I think that other theories beyond the standard model look worse than supersymmetry at this point. Anyway, I will discuss the prospects for supersymmetry in light of LHC results, not just the Higgs boson, but also other results at the LHC. I'll also, if I have time, say a little bit about future accelerators. So there's a lot of discussion within the particle physics community at the moment about what might be the most useful next accelerator. Would one want an accelerator to study in more detail the Higgs boson that has been discovered, or would one want some other type of accelerator which could maybe look for other physics beyond the standard model? So I'll try to mention some of those different alternatives. And then finally, if I have time, I may say a few words about the connection with cosmological inflation. So I think the discovery of the Higgs boson, a Higgs boson, has made scalar fields respectable. And of course, the inflaton, perhaps, if it exists, might be another example of such a scalar field. In fact, there are even some theories according to which the inflaton is the Higgs boson. Now, those theories, I think, are rather difficult to maintain, but anyway, at least I want to discuss this connection between inflation and Higgs physics. So I realize that many of you come from very different backgrounds, so I have a couple of very introductory slides at the beginning before getting into more details of the standard model. So the standard model, of course, is something that's been built up over something over 100 years. The first elementary particle to be discovered was the electron, so it's 120 years ago almost. And experiments have established that in parallel with the electron, there are two heavier but very similar particles, the muon discovered in cosmic rays and the tau discovered in accelerators. Then we have the 6 quarks that are the constituents of nuclear matter. And of course, we have corresponding to each of the charged leptons, we have a neutrino. Then we distinguish 4 fundamental forces: gravity, electromagnetism, and the weak and nuclear force. I guess the photon was the second elementary particle to be discovered, or at least postulated, by Einstein in 1905. So I sometimes like to describe what you see on this slide as the cosmic DNA. These particles and their properties somehow encode all the information you need to make all the visible stuff in the universe. You, me, President George Bush, and so on. However, of course, what you see on this slide misses one essential ingredient, and that is, where do particles get their masses from? So the electron has to have a mass, otherwise there would be no atoms. Electrons would travel away from nuclei at the speed of light. You would never make an atom. The quarks have to have masses, otherwise nuclear physics would look completely different. And of course, the W particle, the carrier particle of the weak interactions, has to have a mass. One of the great successes of the Standard Model is that it gives you a unification of the weak and electromagnetic interactions. An essential ingredient in that unification is that the coupling strength of the weak and electromagnetic interactions is similar. But of course, weak interactions are very weak. Why are they weak? They're weak because they're carried by a particle, the W, that weighs as much as a medium-sized nucleus. So I would say that the biggest problem within the Standard Model, since it was formulated, has been to understand where these particle masses come from, and in particular, where the W mass comes from. And this is the problem which presumably was finally solved in 2012. So you can argue about whether the discovery of the Higgs boson somehow completes the Standard Model, or whether it is a portal to new physics beyond the Standard Model. Of course, if this particle that's been discovered turns out to differ from the predictions of the Standard Model, for example, if it turns out to be a composite particle, then that's certainly evidence for physics, new physics beyond the Standard Model. And I think that's still an open question, although the particle that's been discovered resembles in many ways the Standard Model Higgs boson, as I will discuss in more detail in these lectures. But of course, there are many other problems beyond the Standard Model. For example, why are there so many different types of fundamental particle? Why are there 6 quarks, for example? Why are there 3 neutrinos? Of course, there's many theories that try to give explanations of that, some of them based in string theory. But I think it's fair to say that there is no evidence in favor of any of those theories at the moment. then those of you who study cosmology know that, of course, the universe has lots of dark matter in it. There's something like 5 or 10 times as much dark matter as visible matter. Now, we don't know what that dark matter is made of. Maybe it's made of some sort of astrophysical object that we haven't identified. Or maybe it's made of particles. If it is made of particles, perhaps those are particles that we could discover at the LHC or some other accelerator. These particles would have to be different from standard model particles. They would have to be weakly interacting, they would have to be massive, they'd have to be some new distinctive type of particle, maybe supersymmetric particles. And I'll discuss this possibility later on in my lecture. Of course, we would like eventually to unify all the fundamental forces, not just the weak and electromagnetic forces that are unified within the standard model, but also the strong interactions and, of course, eventually also gravity. So this, of course, is the dream in string theory, although a dream which has not yet been realized in a way that one can test experimentally. And, of course, one would like to make a quantum theory of gravity. I don't need to say that to people here. So the Higgs, or I call it the Higgs, although perhaps I should just call it the particle that was discovered in July 2012. But let me call it the Higgs. The Higgs could be a key to answering many of these other questions. For example, there are theories according to which CP violation in the Higgs sector of the theory is responsible for generating matter-antimatter asymmetry at the electroweak scale, and that asymmetry is made possible by having a large number of different types of matter particles. Many of the theories of dark matter particles are related to the mechanism of electroweak symmetry breaking. For example, supersymmetry. So as you know, supersymmetry, it has been suggested, might help stabilize the electroweak scale. Many theories of supersymmetry contain a stable particle that could be the dark matter. But there are other theories which have also been introduced to try to explain the electroweak scale that also predict similar stable particles, some models with extra dimensions, for example. So I think that this discovery of a Higgs boson potentially could provide us clues to some of these other problems. So let's, I guess, just remind ourselves in very basic terms about why we need a Higgs or something like it, and what at least some of the alternatives were. So we need to find some way of distinguishing between the particles of the standard model. For example, constructing a theory in which the photon is massless, but the W is heavy. So, of course, from a mathematical point of view, that means that we have to find some way of breaking the underlying symmetry in the standard model. So I'll discuss the symmetry of the standard model in more detail in a moment. We have to find some consistent way of breaking that symmetry. So in fact, back when the photon and the W and the Z particle were initially proposed, people just broke this symmetry in the equations. They just wrote down equations which made it impossible to calculate quantum effects. So this breaking symmetry actually in the equations is surely not the thing to do. Instead, what Weinberg and Salam did in 1967, 1968 was to use the idea proposed by Englert, Brout, and Higgs to look for asymmetric solutions of symmetric equations. Now, of course, until the discovery of this new particle, people did consider other possible ways of breaking electroweak symmetry. So what you do in the Englert-Brout-Higgs mechanism, of course, is that you postulate an asymmetric solution to symmetric equations, a broken symmetry throughout all space. Another alternative which was suggested, and in some sense it was quite popular during the first decade of this millennium, was to say, well, maybe you break the symmetry at the edge of space. You break the electroweak symmetry at the boundary. Now, of course, in 4 dimensions, we don't have boundaries. 3-dimensional space, as far as we can tell, goes out to infinity, and if it has a boundary somewhere, that seems to be irrelevant to local physics. And that then led people to consider the possibility of extra dimensions of space with different properties of the different particles in those extra dimensions. For example, different boundary conditions at the ends of these extra compactified dimensions. Now, those theories, I think, are also not looking very healthy. There's no sign at the LHC of extra dimensions. And in fact, in many of those scenarios, there would not have been a Higgs-like particle. People were postulating a decade ago Higgs-less models. So I would say that there were proposed alternatives to the Englert-Brout-Higgs mechanism. But at the moment, those models look very sick. I'd also like to show this little slide here just to cheer up my friends who, like myself, still believe in supersymmetry. So what this slide shows you is the number of years between the postulation of a particle and its discovery. So, for example, the tau lepton, that was not proposed before it was discovered, so the time gap is 0. On the other hand, the gluon was postulated maybe 10 or 15 years before it was actually discovered. So if you look at all these, the longest time lapse between proposal and discovery was, of course, the Higgs boson. That was a time lapse of 48 years, which gave time to Peter Higgs to evolve from this picture actually, that's not quite true. This is actually his passport photograph. It was a little bit before he actually wrote down his theory. But by the way, one thing which I forgot to mention about this slide is that it was compiled by The Economist, which is a British financial magazine. So it shows you that this discovery seems to be noticed in the outside world. Anyway, like I said, there were 48 years between the proposal of the Higgs boson and its discovery, and we supersymmetrists should remember that supersymmetric particle physics started in 1973 with the work of Weston Zumino. So far, it's only been a little over 40 years. So keep the faith. Okay, after that general blah, 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 now let's get down to work. So let me first of all remind you of the structure of the Standard Model. So we have these three charged leptons, electron, mu, and tau, and each of those is accompanied by a neutrino. And the left-handed charged leptons and the neutrinos are grouped into doublets of the SU2 group. The right-handed components of the electron, mu, and tau are singlets of SU2. There's a similar structure for quarks. We get doublets of left-handed quarks, up, down, charm strange, top, bottom, and then the right-handed components are singlets. And over here, I've written the SU3, SU2, and U1 of hypercharge quantum numbers of the elementary particles. Now, I'm sure that many of you are thinking that this structure looks rather random. You know, who ordered this particular set of quantum numbers? Why on earth does this particle over here have a hypercharge of 4/3, and so on? You are right to ask that question. You are right to criticize the Standard Model for being a mess. And there has to be some sort of more fundamental theory behind it, some sort of unified theory which would explain those quantum numbers. But in all honesty, at the moment, we don't have a good explanation. We have lots of ideas, but we don't have a good explanation. So for the purposes of these lectures, you're just going to have to accept that on the basis of trust. But of course, your job, you students, is to come up with something better, okay? So the Lagrangian of the Standard Model has this well-known form. So here we've got the strengths of the various different gauge interactions. Here we've got the interactions of those forces with matter fermions. Here we have the term that was conjectured to give masses to the fundamental fermions, so-called Yukawa interactions. And here at the bottom, we have the kinetic term and the Higgs potential for the Higgs field. So the forms of the first two terms here, the first two lines, are essentially determined by the gauge symmetries. Once you've specified the gauge symmetries of the quantum numbers, then you know exactly what the first two lines should be. And experiments over decades confirmed those predictions with a precision at the per mil level. And later on in this lecture, I will discuss a little bit those experimental checks on the first two lines of the standard model Lagrangian. Then what I'll talk about is the two bottom lines. These are the two lines that until July the 4th, 2012, were conjecture. And these are pieces that are not so constrained by the gauge principle. So, for example, these Yukawa interactions are not constrained at all. Those coefficients y could be almost anything. And again, there's a big problem to understand why they have the values that they do. And if I look at the bottom line, the kinetic term for the Higgs field, that's, of course, determined, but the effective potential is not. And we postulate an effective potential that gives you spontaneous electroweak symmetry breaking. But within the standard model, that's just a postulate. Of course, we would like to have a theory that explains the form of the effective potential. And there are some ideas for doing that in supersymmetry, and I hope to mention those in a later lecture. So the standard model agrees, I would say, perfectly with all the confirmed accelerator data. Of course, every once in a while, somebody comes along with some crazy experiment that finds some discrepancy. But usually, up until now, those discrepancies have eventually gone away. And that agreement, which has been building over perhaps 30 years, really seemed to indicate, even before the Higgs discovery, that something very much like a Higgs boson had to exist. If you didn't have something like a Higgs boson, then you would not be able to get sensible results to compare with the experiment. Moreover, those comparisons between theory and experiment indicated that the Higgs boson, or whatever replaced it, should have a mass, let's say, less than a couple of hundred GeV within the range accessible to the LHC. That's why there was a good deal of optimism before the LHC started that indeed the Higgs boson, or something replacing it, would be discovered. Let me just show you one slide which gives you some flavor for this agreement between the standard model predictions and the measurements. So what I show here on the left-hand side is a comparison between the measurements of the couplings of leptons to the Z particle, the carrier particle of neutral weak interactions. Comparison between the measurements represented by the ellipses and the standard model calculation, which is represented by this yellow sort of bent triangle here. So many, many measurements of different leptons. You average them all together, and you have this black ellipse here. So this is the preferred range inside that ellipse. And you can see that those measurements have an accuracy of better than 1%, per mil, something like that. So this here, as I said, represents the theoretical prediction. Now, the theoretical prediction for these measurements depends on the masses of heavy particles. Depends on the mass of the Higgs boson, depends on the mass of the top quark. I'll come back to that in more detail later on. But what you can see from this is that the data certainly seem to prefer a relatively small mass of the Higgs boson. So this yellow region, calculations were done with a Higgs boson weighing perhaps as large as 1 TeV. But you see from this that a small value seems to be preferred. So that's just one example. There's many, many other examples of measurements that have been made. And over here on the right-hand side, this is a long, long list of comparisons between experimental measurements and the predictions of the standard model. So remember, of course, every experiment has a measurement error, and you wouldn't expect all the measurements, all the central values of those measurements to agree exactly. I mean, they should fluctuate backwards and forwards. And that's indeed what you see here. That, most of the measurements agree within 1 standard deviation, sometimes 2. There's even one which is almost 3 standard deviations away, but that's statistically completely reasonable. Generally, the standard model works extremely well. Okay. So this is the standard model Lagrangian in a bit more detail. So inside this box here, we have the piece concerning gauge interactions and the way that those interactions act on the fundamental fermions. So as we saw on the previous slide, those predictions have been confirmed at better than the percent level. And this, in the red box here, as I said, this is the piece involving the Higgs boson. This is the piece for which there was no direct evidence until 2012. And the next order of business is perhaps to check these terms here in the effective Lagrangian. Perhaps we can check them as accurately as these terms in the green box, or perhaps we will discover that there is some discrepancy in the red box, which will be evidence for new physics beyond the standard model. So I've talked about the Higgs boson. I've talked loosely about the Higgs mechanism for breaking electroweak symmetry. But of course, as you all know, the work that Peter Higgs and others did was in a context which also involved many other theoretical physicists, and in fact had its roots in condensed matter physics. So here I've written what's probably a partial list of the initials of people who are involved in this, including, actually excluding, I don't seem to have got Nambu in that list. Oh dear. Anyway, Anderson, for example. So there are ideas about spontaneous spontaneous symmetry breaking that were present in condensed matter physics, in particular in the interpretation of superconductivity, in particular by Nambu and Anderson. But those ideas were introduced into particle physics, first of all by Englert and Brout, and then subsequently by Peter Higgs, subsequently and independently by Peter Higgs in the same year. There was also a third group, Guralnik, Hagen, and Kibble, who also worked on spontaneous symmetry breaking a bit later in 1964, although when they wrote their paper, they acknowledge, they refer to these previous papers by Englert, Brout, and Higgs. I would like to also mention a less well-known paper by two young Russian theorists. Is there anybody here who is under 19? No? So then you're too old. Migdal and Polyakov independently invented spontaneous symmetry breaking when they were students, just 19 years old. But the big bosses in the Soviet Academy of Sciences refused to allow them to publish their paper for some time. So it was delayed, and so their publication date is actually significantly later than these other ones. But if you look at that paper, it's actually quite remarkable. It has spontaneous breaking of non-abelian gauge theories, in fact, earlier than anybody else did. So with all these people involved, you might ask yourself, well, why do we call it the Higgs boson? And the answer is that of all these people, Higgs was the only one who actually mentioned that there should be this massive scalar particle. Okay, this is a little historical summary. I don't know whether I'm going to discuss this in great detail, except just to note that Peter Higgs's crucial paper, where he predicted the existence of this massive scalar particle, was actually initially rejected by the journal. He submitted it to Physics Letters, and one of my distinguished colleagues at CERN, I wasn't at CERN at the time, but I became his colleague later on, decided this paper was not interesting. And so Peter Higgs revised the paper and sent it to Phys Rev Letters, where it was accepted. Nambu was a referee. I don't know who was the referee for Physics Letters. Anyway, as I said, Higgs was the only one of all these initial authors who pointed out the existence of this massive scalar particle. And it all boils down to equation 2b in his paper. So if you have a telescope or very good eyesight, you will see that equation 2b has the form of a Klein-Gordon equation with a mass term, which is given by the second derivative of the effective potential. So this is the equation of motion for what we now call Higgs boson. On the other hand, if you look at the corresponding equation, for example, in the paper by Guralnik, Hagen, and Kibble, then there is no mass. And there was no discussion of this at all in the paper by Engler and Brout. By the way, I would like to just mention Robert Brout. He, of course, was the collaborator of Engler, and he surely would have shared in the Nobel Prize that was awarded last year if he had lived. But unfortunately, the delay was too long for him. Okay. Perhaps just a couple of words about the significance of the Higgs boson discovery. Of course, it's not true to say that the Higgs boson gives masses to other particles. It's the Engler-Brout-Higgs field that gives masses to other particles. And the Higgs boson is the quantum of that field in the same sense that the photon is the quantum of the electromagnetic field. And the significance of the Higgs boson discovery is that there was no evidence for the existence of this Engler-Brout Higgs field until you found the associated quantum. So let's remind ourselves in a bit more detail of what this, I've called here the Higgs mechanism, should be the Englert-Brout-Higgs mechanism, works. Okay, so here is a picture of the form of effective potential which was postulated by Higgs et al. So it's renormalizable, so it's a combination of a quartic and a quadratic term. The coefficient of the quartic term has to be positive, otherwise the vacuum would be unstable. We'll come back to that point later on. This has to be positive. This quadratic term could be positive or negative. So what happens if it's negative? If it's negative, you get this form for the effective potential where the origin is unstable and the stable configuration has this circular shape around the bottom of the potential. It's often compared to a Mexican hat. And we'll come back to that Mexican hat analogy later on. So the minimum energy configuration, of course, is at a non-zero value of the Higgs field with a value which is given by this coefficient and the quartic coefficient. The phase of the expectation value of the Higgs is, of course, arbitrary. So you've got two components of the Higgs field in this simple model. One component which corresponds to the phase degree of freedom going around the potential, and another one which is the radial degree of freedom corresponding to going up and down the sides of the potential. So since the degree of freedom going around doesn't change the energy, that component has zero mass. Whereas the radial component, since it does change the energy, does have mass. And that is what we call the Higgs boson. So, many people say, well, but this is trivial, right? Well, yes, it is trivial, but it's important. And if you did not have this non-trivial radial shape of the potential, then you would not have a fixed vacuum expectation value, and you would not have electroweak symmetry breaking. And that's the significance of the Higgs boson, that it tells you that you've got the right idea, the right mechanism for breaking electroweak symmetry. Now, in the standard model, this Higgs field also couples to fermions and gives them, I'm not sure what that is, that's supposed to be non-zero masses, which are related, as I mentioned earlier on, to those Yukawa couplings. Actually, the first person to point out that the same Higgs field that gives masses to the massive vector bosons could also give masses to fermions. The first person to point that out was actually Steve Weinberg in his 1967 paper. Okay, now, what happens when you incorporate gauge fields into that model that I had on the previous slide? So this is the abelian case. So this is the kinetic term for the Higgs boson, the potential that we saw before, abelian gauge field strengths, abelian covariant derivative. So we can always make gauge transformation. And that gauge transformation enables us to rewrite the Lagrangian in this form here, where you can see explicitly that you've got a mass term for this gauge field A mu, and the mass term for this is related to the expectation value of the, sorry, because it's term down here. This mass term for the gauge field is explicitly related to the vacuum expectation value. It's the vacuum expectation value of the Higgs field multiplied by the gauge coupling strength. So what happens is that the massless phase degree of freedom combines with the massless gauge boson to give you a massive gauge boson. And of course, you still have this massive scalar boson, which is what we call the Higgs boson. So a little bit more about how these ideas were introduced into particle physics. In fact, the person who introduced ideas of spontaneous symmetry breaking into particle physics was Nambu, although what he considered was spontaneous breaking of a global symmetry. So for him, this massless degree of freedom going around the bottom of the potential was actually a physical degree of freedom. And that, of course, was his interpretation of the pion in QCD as an almost massless Nambu-Goldstone boson. Goldstone, because Goldstone gave a mathematical model for this. Actually, this Mexican hat potential that I showed you was basically Goldstone's model. So what was shown by Englert, Braut, Higgs, Gralnick, Hagen, and Kibble was, as I discussed on the previous slide, that this massless degree of freedom going around the bottom of the potential could be combined with a massless abelian gauge boson to become a massive gauge particle. And as I've tried to emphasize, the small, trivial piece of additional value that Higgs added was to point out that in a model of this type, you would necessarily have this massive scalar particle corresponding to the radial degree of freedom. So the basic idea for spontaneous symmetry breaking in a relativistic theory was shared by Englert, Braut, and Higgs, but as I said, only Higgs observed that you had to have this massive scalar particle, and the significance of that particle is not so much that it gives masses, but that it is a signature of that mass donation mechanism. So that was the abelian case. So the standard model is a bit more complicated, of course, because you've got SU2 and U1 gauge bosons. You've got a very similar kinetic term for the Higgs field, although now, of course, the covariant derivative has an SU2 as well as a U1 piece in it. But in the same way as before, you postulate an effective potential that has a non-trivial minimum. You expand the fields around that minimum, and again you get a quadratic mass term for the charged vector boson W. Situation for neutral vector bosons is a bit more complicated, because of course you've got two of them. This was what was originally postulated by Glashow back in 1961. In addition to the photon, you've got a neutral gauge boson, which is the neutral member of an SU2 triplet. And this neutral boson W3 mixes with the U1 gauge boson B. But if you look at these quadratic mass terms, you see that they have the form of a perfect square. So there is one combination of neutral gauge bosons that has a mass and one combination that has zero mass. So this is unfortunately squeezed down the bottom of the slide. But if you diagonalize the neutral gauge boson mass terms here, then you get one state which has a mass, a bit larger than the W, and one which has zero mass. And of course, the one that has zero mass we identify as the photon. So the mechanism works in precisely the same way as in the simple U1 case, but you have this additional feature of mixing. That mixing actually is potentially very interesting because it may provide us with a clue about eventual unification of the fundamental interactions. So I don't have time to discuss this in these lectures, but the magnitude of that mixing is actually a prediction of many unified theories and can be used as a way to probe them. So as I said, the Higgs has couplings not only to the massive vector bosons, but also to fermions. These are the couplings that were first observed by Steve Weinberg. This means that the decay rate of the Higgs to fermions is proportional to the fermion mass squared. The decay rate into massive vector bosons will be given by this formula here. In fact, Peter Higgs wrote a third paper. He wrote two papers in 1964, but he wrote a third paper in 1965. In fact, that was the paper that he was working on in the picture that I showed on the very first slide. So in the very first slide, he was actually working out in some detail the phenomenology of the Higgs boson. And for example, he calculated the decay rate of his boson into massive vectors. And he really took this idea seriously, whereas the other guys, Englert and Brout, also Graunik and Hagen, essentially dropped these ideas after 1964. But Peter Higgs paid attention to it. Now, I'd just like to take out a moment to explain in somewhat different terms why something like the Higgs boson is needed. I mean, some people have said, well, this Higgs mechanism looks, again, very untidy. It doesn't look like a very beautiful theory. Surely there must be some alternative. But consider what would happen if you scattered two massive vector bosons off each other. And this may sound like a very abstract experiment, but in fact, in some sense, the LHC is performing that experiment. So you know that if you scatter W particles off each other, there has to be diagrams with the exchange of photons and Z bosons. But if you just calculated the scattering with the exchanges of photons and Z bosons, and if you calculated the scattering matrix element, you would find that it would grow at high energies. This would then give you a problem if you try to calculate a loop diagram. So you imagine trying to close this loop and so you take the square, which is what you would have to do. Then you're going to get infinity, because you have to integrate over the intermediate energies and momenta, and that's going to give you an uncontrollable infinity. The only way of cancelling out that bad high energy behavior, the only way of getting a loop diagram that you can calculate, the only way is to put in an additional scalar particle. And moreover, in order to cancel out that high energy behavior correctly, that scalar particle has to have the standard model Higgs couplings to the massive vector boson. And in fact, there was a whole literature in the early 1970s where people proved that essentially the only way to get a calculable, renormalizable model with massive vector bosons, the only way to do it was to postulate, in addition, a scalar particle. And this slide talks about the case with massive vector bosons, but it's the same thing with massive fermions.
Naive question to you about that,
Yeah.
which is, couldn't it have also been possible to control these infinities in an extension of the standard model that didn't involve a scalar, for example, with a strongly coupled sector, like some version of Technicolor, just at the level of trying to tame the renormalizability problem?
So if you would need something which, if you do a partial wave analysis, appears in the spin zero channel. Right? Whatever appears in the spin zero channel would have to have couplings, for example, to fermions proportional to their masses.
So it could have been something like the Techni rho or something, but in other words,
It would have to be something more complicated than the Techni rho. Well, the Techni rho, of course, would have been a vector particle. But in a model, I'm going to discuss models of dynamical symmetry breaking in my second lecture. Okay. But in those models, you would have had to have had a spin zero particle, which of course you have, we believe, in QCD, although it's difficult to identify. So technically sigma, like the technical. To give masses to fermions in a consistent way in such a theory was much more complicated. What am I doing for time a little bit?
5 minutes.
5 minutes. So my own personal interest in the Higgs boson started in 1975. So that was the time when the standard model was just beginning to be thought about in some sense as a serious theory. But with Mary Gaillard and Dimitri Nanopoulos, we convinced ourselves that the key thing that you had to check to see whether this mechanism was right was whether or not there was a Higgs boson. And so we wrote a long paper discussing what this Higgs boson might look like. Of course, it was still speculative at that stage, and nobody had any idea what the mass of the Higgs boson might be. So that's why we finished our paper with the sentence that we do not want to encourage big experimental searches for the Higgs boson. Fortunately, people did not take our advice. So there were various accelerators that tried to find the Higgs boson. Of course, the one that found it was the LHC. And I can't resist showing these plots, which are from a paper which I wrote with Henry Kowalski and Graciela Gelmini 30 years ago, and there was the first workshop on LHC physics, and we had a long section there about how you would put the Higgs boson at the LHC. So I mentioned earlier on that before the Higgs boson was discovered, there were estimates of how heavy the Higgs boson should be. And the way that those estimates were made was to look at quantum effects, loop effects in the standard model. So I showed you some observables in the standard model earlier on. Now, here, for example, is the mass of the W or the mass of the Z boson. And I showed you earlier on the formula at the classical level, which just corresponds to the 1 here. But there's a radiative correction called delta R, and that and other radiative corrections are sensitive to the masses of heavy particles. So if you didn't put in a heavy particle, if you didn't put in the top quark, for example, then the theory would not be renormalizable, and that radiative correction would be infinite. Correspondingly, if you put in a finite mass for the top quark, you're going to get a finite correction, but it's proportional to m top squared. Similarly for the Higgs boson. If you didn't put in the Higgs boson, you'd get infinity. If you put in a finite mass, you get a finite correction, but it grows logarithmically with the mass of the Higgs boson. So if you measure the masses and other properties very accurately, then you can hope to disentangle the mass of the top quark and the mass of the Higgs boson. And in fact, before the Higgs boson was discovered, those calculations indicated that the Higgs probably weighed around 100 GeV, perhaps with an uncertainty of 30 GeV or so. As I mentioned, there were previous searches for the Higgs boson, for example, in the Large Electron Positron Accelerator at CERN, which established a lower limit, again, of around 100 GeV, a bit more. And of course, also the Fermilab Tevatron Accelerator also looked for the Higgs boson. And in the period before the LHC got started, they were also able to exclude a range of masses around 160, 170 GeV. So that's all summarized on this picture here. So the yellow region is what was excluded by LEP experiments. The yellow region over here was that excluded by searches at the Fermilab Tevatron. And those precision electroweak data give you a preference for Higgs boson at the bottom of this parabola here, around 100 GeV. So probably you shouldn't believe all these figures too much. They're not all significant. But the indications were the Higgs boson should be relatively light and accessible to the LHC. This is a compilation of those results. So this shows you the global chi-squared function, so the likelihood function. So this gray shaded region over here, that's excluded by LEP, excluded by the Tevatron. And this line here corresponds to the likelihood function that you get by combining those exclusions with the precision electroweak measurements. So this was a combination that was done by the GFITR collaboration, a group of experimentalists, back in 2011. And they actually predicted that the mass of the Higgs boson, based on previous data, should be 125 plus or minus 10 GeV. So prediction turned out to be right. And a cynic might say that all that's happened since then has been the uncertainty has been reduced by a factor of 10. So perhaps I just finish by saying a few words about how the Higgs boson is produced and how it decays at the LHC. So the LHC, you collide protons at very high energies. Those protons contain various constituents, gluons, quarks, and so on. And the dominant way of producing the Higgs boson is actually through collisions of two gluons, which is interesting, because you might say, well, the particles acquire their masses from the Englert-Brout Higgs field. The couplings of the Higgs boson are proportional to masses, but the gluon has no mass. So how come gluons can produce a Higgs boson? And that comes about because of loop effects, in particular loop with a top quark. And that loop is sensitive to other particles, and in my second lecture we will discuss constraints that you get on other particles from the agreement between theory and experiment. Then there are processes where when you collide two protons, they radiate two W particles, and those W particles collide to make a Higgs boson. That's this WW scattering process that I mentioned a few slides back. So this is now something that's starting to be measured at the LHC. And then there are processes where the Higgs boson can be produced in association with a W particle or with a TT bar pair, although the evidence for those processes is not so strong at the present time. Somebody up there loves particle physicists, because if the Higgs mass is around 125 GeV, all these different production modes are observable. So there's many things that we can measure, and that enables us to characterize the properties of the Higgs boson. If it had weighed, let's say, 600 GeV, then we wouldn't have been able to observe these processes over here. Our information would have been very limited. We're lucky. So I would like just briefly to pay tribute to my theoretical colleagues who calculate these processes with high accuracy. I mean, it's one thing to write down a tree-level diagram and calculate it, but these guys go away and calculate two-loop quantum corrections, and many thousands of man-hours of work go into refining these predictions. And these refinements in these predictions are absolutely crucial when you come to try to characterize this new particle and tell whether it really is standard model-like or not. So the final thing which I wanted to discuss was how the Higgs boson decays. So the couplings of this particle generally are proportional to their masses. And that means that generally it prefers to decay into heavy particles. For example, if it weighed 300 GeV, it would decay essentially every time into W pairs and Z pairs, as calculated by Peter Higgs in 1965. In fact, with a mass of 125 GeV, many other decay modes come into play. Decays into boson quarks, tau, leptons, charm quarks, and also into gluons. So couplings to gluons, these are very important quantum loop corrections. Similarly, decays into photons. The same sort of diagram appears there. Actually, this is one of the things that we calculated in our paper back in 1975. And that, of course, was one of the key decay signatures of the Higgs boson observed at the LHC. So again, somebody up there loves us because with a mass of 125, you can observe all these different decay modes. And that means that already we know a lot about the properties of this new particle, and that's going to be mainly what I discuss in my second lecture.
Thank you, John, very much.
It has to be turned on.
Okay, we have time for a few questions before we break for the tea. Other questions?
So the Higgs mass is much less than the combined mass of these two vector bosons and stuff. So how does it decay into 2W or 2Z? I mean, onshore.
Okay. So in fact, it doesn't decay into two on-shell vector bosons. It decays into, well, usually one on-shell and one off-shell. In fact, if you do the calculation properly, you also have to take into account two off-shell vector bosons. This is done correctly. And in fact, precisely because at least one of those vector bosons is off-shell, that's why the decay rate declares the vector boson drops off here.
Any other question? Okay, if there are no questions, let's ask. And let's thank John once again.